All right, from our earlier lectures on here, all our earlier videos, you remember that there was a lot of emphasis on doing normality testing to make sure that we're using the appropriate statistical tests, like t-tests for normal data, Mann-Whitney test for non-parametric, or Pearson correlation for normal, Spearman correlation for not normal. Well, with linear regression, the assumption is that the data are normal, but there are a variety of other assumptions, and we need to be able to figure out how to test the various assumptions. So that's the focus of this video. Now remember our previous video, we had a statistical model that had all of these terms that were statistically significant. Now there's additional courses, more advanced statistics classes where you may go into actually model building, where you may have a lot of variables and then you may go backwards one by one, removing them from the highest p-value to the lowest p-value until all your terms are statistically significant. And in the case of biostatistics, the only terms that should be in your model are ones where there is some sort of biological or sociological reason for why you think that these terms that are here are actually predictive or useful for understanding their impact on life expectancy or assessing whether or not they are significant terms for influencing, your outcome variable. So say we have a model, say this is our best fit model. I'm sure we could come up with better ones if we were to invest more time in it or had a particular project that we were interested in. But say this is our best model for predicting life expectancy for the U.S. counties in the United States. So here we go. We've got this as our model. Now we need to check the assumptions. And we have our previous line equation. We don't necessarily need this equation for assessing the assumptions, but that would be the equation. If we rush through it at the end of the last video, I want you to just be familiar that, this is a multivariable equation, so y equals m1 x1 plus m2 x2 and so forth. Now, for assessing our model as it relates to the assumptions, we have particularly these 5 major assumptions. Some people may say 7 or 10, but there are these 5 major assumptions in my mind that need to be met, assuming that you had from here y needs to be a continuous variable. So you have that. Some people call that an assumption, but I think that you go into it knowing that you should use a continuous variable for your y. Now with regards to the actual model, we need to ask ourselves, are our data behaving as normally distributed data? So we have to check the normal assumption. We have to see if our model, or at least our fitted model, looks like it's linear, because this is linear regression. We also need to check our model to see how well it actually predicts for every county in the United States, or see if we've got any major outliers. We need to make sure that these individual x variables, these x's, like income, smoking, auto mortality rate, we need to make sure that rural, diabetes, that these are all acting independently. They're not explaining the same thing. Because, smoking is associated with low income. We want to make sure that this is actually acting independently of income and not overly collinear or overly kind of correlated with one another. That these are truly independently providing information. The fact that these were statistically significant, that already helps demonstrate, though, that they are contributing new information or new knowledge with regards to the ability to increase our R-squared and better predict life expectancy. So that helps. Things that are collinear tend to knock each other out, but that's not always the case. So we have to make sure that our x variables are acting independently with little to no collinearity. And then lastly, there's this interesting statistics word that's used a lot. We need to look at our data and see if our data meet the homoscedasticity assumption. So we need to make sure that our data meet the homoscedasticity assumption, which really just means that from our highest values to our lowest values, that there's an equal amount of variability for the low values and the high values, and this will make more sense once you graphically see it. So we're going to go through these major assumptions. It may look terrible here, but they're actually very easy to check. So the first thing we need to do, so we're ready to check our assumptions, is we need to generate a new column in Stata for our residuals. And our residuals largely are just our model fit departures from the true value. And we need to generate a new column in Stata for our actual fitted model, our line of best fit, our multivariable line of best fit. There's a single line that we can actually make around all those dots. All right. So we run our regression command like you would usually. So you have to do this first. If this is the last regression you ran, then you can just skip to the next step. But you've got to run your regression command with all your variables. Make sure this is the model that you want. And then we will predict our fits. And we can type predict, and we could write anything. You could type model fits. You could type p hat, which is what some people will put for predict p hat. You could put predict modeled data, whatever you want, but predict fits. By typing predict and then this, it will generate our fitted values. Next, we want to predict our residuals. And in order to predict our residuals, we have to type in predict, and then we give it whatever name we want, comma, residuals. So we have to type in the comma and residuals. This comma residuals tells it to make this newly created column our residuals column. So we've got two new columns, the fits and residuals columns, that will be created in Stata. So they will go on to the very end of your spreadsheet in your data editor, and you can see here is a column for residuals, here's a column for fits. These fits are what our statistical model thinks or suggests or predicts the life expectancy to be, and the residuals relate back to the difference between this fitted data and the actual true data that were observed or reported for our y variable, for our outcome. So it's comparing our predicted versus our y value that's captured in the residuals. So the data have to behave as normal data. So how do we check that? We've got all them different variables. How do we check it for the whole model? It's very simple. Since it's multivariable, we will do the normality test on the residuals. If we have more than 2,000, we should use this S Francia res1 command. So we do the Shapiro-Francia test on our residuals, and we see this really low p-value. Remember, low p-values from normality tests tell us that our data fail to meet the normal assumption. Our residuals are statistically different from the normal distribution that we would expect. So we fail the normality assumption. So the data behave as normal data, not here. That failed. All right, next one. Do the model fits. The actual predicted values appear to be linear, and do we have major outliers or not? So how do we do that? Well, we've already created back here predict fits, and we also have this predict residuals. We're going to use these here in a second. So we've already used residuals for the normality test. Now we're going to check for linearity and major outliers. We're going to just do this visually for this purpose, for here. So this seems to be a pretty linear relationship. Would you say? There's no bow tie shaped pattern or S, or it looks like a good linear relationship between life expectancy and our model predicted values. What about outliers? So here, this is way off the mark of the middle value. Look at this. This value, we expect this county to have had a life expectancy of about 79 years, but what was actually observed was like 67 or 68. This county, we had a life expectancy you'd expect of about 77, when in fact it's actually more like 67. So these values are definitely outliers. We got a variety of outliers. Up here, this county, we expected it to be about 83 years of age, and it's like 87. So this is a positive deviant. These are negative deviants. We could learn a lot maybe from that community, or what are they doing up there to be healthier, but it's not fitting our statistical model as well as a linear relationship would want it to. This one's not as bad though as this one. This one's terrible. I mean, it's not even close. As well as this one. For whatever reason, we only expected these people to live to 71, and holy cow, they're 80, 81. So this is another great positive deviant. So you can learn a lot qualitatively about these positive deviants, but from a statistical model, these are outliers, and we could redact them from our data set, which is problematic, or you can keep them and just live on with it. So there's a lot to be dealt with, and it's complicated on how you manage or deal with residuals. So that was plotting life expectancy versus our fitted values. All right, now we could plot our residuals if you wanted to, and you can see here we've got some tails here, so these ones are outliers for sure. They're the same values that are probably here. So you can scatter plot life expectancy and residuals and find some outliers there. If you want to, you can look at your data. You can actually look. You can do a sort command and rank them from lowest to highest. So this one's got a -12. It's the highest residual. So who are these? You can actually look at the column and then go over to the row and see that it's this county in South Dakota. I think it's an Indian reservation where suicide rates are really high. So they've got a big outlier. We see Perry County, Hazard, Kentucky. It's life expectancy from the model was supposed to be 74, but they're not performing as well. Their life expectancy was 70.6. We see Owsley County. We had expected it to be 74.85, but they're at 70. This first county, the Pennington County, we expect 79.65 years based off of age, or based off of smoking, based off of income, and so forth. In fact, though, they're only 66.81. So these high residuals here, you can have a cut point and kick them out of your data set, or you can keep them in and just acknowledge it. So we failed our normality test. We appeared to pass our linearity test, but we had several outliers. What about collinearity? Are any of the variables explaining the same amount of information? And this is a super easy command. After you've done your regression, just type in VIF. Once you do that, you want low VIF values. The general rule of thumb is if the mean VIF value is under 5 and none of these are over 10, you're in good shape. So these are all acting pretty independent of one another. No evidence of collinearity or little evidence of collinearity. So we have low VIF values, so we did great there. VIF, very easy command to do, very easy to check on linear regression. So we passed that one. The last one, do our data meet the homoscedasticity assumption? Hard word to say. So what we do for that is we scatter plot the residuals versus the model fits. We look at this and we look to see, is there more variation here or more variation here? Is there any particular pattern? Is it pretty consistent amount of variation? This is a visual call for this class. I took this image from this website here because I think it's the best one out there. This kind of random cloud with no pattern is what we want. Patterned stuff where it funnels or where it has a bow tie shape, these are bad. So if we go back and look, it funnels a little bit, but it's still pretty good. It's closer to this, in my opinion, than these. But there is some degree of funneling here, and there's definitely a lot of fanning out on this side. So it's, if you removed the outliers, maybe, so it's kind of hard to call it. So it mostly meets it, in my opinion, but that's a judgment call. So what happens if you don't meet the assumptions? Well, you can construct new models and use different terms. You could drop a term, you can log transform, You could admit your challenges and go on. You could say that your model is weak, or just don't do linear regression. But that's all.